3, 2, 1, go. We're live. This is Retraice segment number 76 for Saturday, December 10th, 2022 at 11 p.m. Eastern, 8 p.m. Pacific. Retraice is about what's going on out there. The short answer to that is computer control. The long answer to that is not worth going into right now. Yesterday, we placed an airport. Today, we're going to slide that airport right into place. What are we talking about? AIMA4e, Artificial Intelligence and Modern Approach, Russell and Norvig, 4th edition. We're doing the math, we're doing the code. This is the December to Remember Math and Code event. You should have already known. We're on segment number 7 of this. Why don't you know that? Anyway, it doesn't matter. Today, well, I'm kind of chuffed. Do you know what chuffed means? Go look it up. I'm kind of chuffed with myself because of what you're about to behold. I thought this was going to take a couple days. Got her done. What you're looking at here is that sliding I was talking about. This is our first airport guess, 1811. Today, got done that second airport guess, 1710. I'll explain how I got to that in a second. And then bang, number 3. Right on target. And our objective function gives 37, which we know through other means is the best score we can get. Okay, so that's what the graphical version of this looks like, and I'm going to go into some of these little comments around the graphical. Here's the, what the hell is that? This is the hand math, I'll call it. The hand math. There will be plenty of this in the future of Retraice. This is the hand math that I had to do to slide that airport right into place. And over here is some spreadsheet math that I also had to do to confirm that we had slid it correctly into place, okay? So I'm going to kind of just overview it. You can go through and inspect it. I think it's pretty easy, not pretty easy. I mean, it's kind of chicken scratchy, but I couldn't be at the terminal today, so I was doing this out and about around town. So I had to do chicken scratch mode, but I'm kind of glad because I move faster in chicken scratch mode. Putting everything in LaTeX is hard. It's just in 3 columns, so you start at the top of the first column, you work your way down. Anything I've struck out over here was not necessary or not relevant to the argument. But basically, I'm just calculating I'm doing the math on the equations we've already talked about. I'm doing our objective function of the first guess airport is state X. I put a little bar over the X's here because I used bold not to represent vectors, so it has a bar over it. It's a vector in this math, but if it's bold, it's not a vector. It's just something I'm trying to call out to myself visually. Then I started calculating the partial derivatives, the partial derivative of f with respect to x sub a. I used a instead of I or whatever I was using for the airport. I used a for airport and plugged it in, blah, blah, blah. I know it's not blah, 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 but like you don't really need me to go through this. If you care about it, you'll go through it and you can see that I did what I said or what I've said I've done. Now, here's one thing. I did have a little moment of scary. After I did the second airport, I found that the polynomial that describes the part of the partial derivative was exactly the same for both partial derivatives. It's this little thing. Actually, it wasn't that one. It was the first one. Yeah, after the first guess, it was, okay, so this polynomial is what we're going to use to do the spreadsheet math. And then I calculated it for f of the vector x with respect to x sub a, partial derivative of f with respect to x sub a. Where did I write that? I had to have written that here. Where's that? Where can I just point to that? Oh, it's up here. Yeah, partial derivative of f with respect to x sub a, which is defined as the limit of this, what would be a sequence. This would be, a sequence. You keep plugging in more and more values for h, and so that it gets closer and closer to 0. That's what I'm doing down here in the spreadsheet. I'm plugging in more and more values for h, closer and closer to 0, and watching the behavior of the rest of the polynomial here. But really what we care about is the full calculation, which amounts to the same thing here, partial derivative of f with respect to x sub a. And at the end of it, we get a slope. And it was +6. But then I got the same polynomial when I differentiated with respect to Why? And I know what you're thinking. What? You're telling me you differentiated with respect to one independent variable, and then you got the same polynomial as part of the limit for a different independent variable? Yes, that's crazy. Did that really happen? Yeah, it really happened. It's crazy. It's really, you don't even know how. Okay, so let me tell you how it happened. it would spook me out, because basically what happened is that shouldn't happen. Like, there's just no reason. I'm doing gradient descent. I must have screwed something up. I must have done something wrong. There's no reason that this polynomial should show up again. I must have, and it took me a little while to, like, a few tens of minutes. I'm thinking, I got to go back through and check everything. And I'm misunderstanding something, whatever. No, here's what I did. I'll show you what I did. It's sort of like good luck, bad luck. So when I picked my cities, first of all, I squeezed this map that the background map here. I squeezed a little bit to fit into my grid here, so that I could work with round numbers. This 14, 13, and 19.6. I wanted to work with round numbers because there's no point calculating at 3 significant digits when you can work with 2. It's just a pain in the butt, and you don't learn anything. And then when I landed my airport, I just said, I don't want it to be like right in the middle, so I'll do it a little bit off center, and I'll put it also on a perfect little grid marker, 18, 11. Okay, that is what did it. I picked, out of all the lines that I could have put this first airport on, there is only one in this whole space of lines, in the infinite space of lines that you do not see plotted here, but that could be every single, in the infinite space of straight lines in all directions. There is only one that I could have put this line on where that polynomial would occur exactly the same for both independent variables, and it would amount to both of them yielding a slope of 6. Okay? Their partial derivative, the partial derivative of f with respect to x sub a and the partial derivative of f with respect to y sub a would both be 6, or both would, the limit, it would be defined in the limit to be 6. And I picked it, and the line is captured by the equation y equals x minus 7. And it's just because, I was trying to pick round numbers, and I just got unlucky. If I had picked the only places that I couldn't pick without having this problem are like here, 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 here. I didn't draw it, but that all through these intersections, that's the line y equals x minus 7. If I'd picked anywhere else, I wouldn't have had this spooky coincidence. But anyway, I kept going to see, okay, is this at least going to, because I was having doubts here. I was like, is my gradient descent actually going to work? So here's the first airport guess with its objective function score of 46. I just followed the advice of the algorithm. I did what it told me to do. Okay, so it said, what does it mean? This is kind of hard to grasp, and I'm only starting to just get used to it. Again, we don't learn mathematics. Nobody understands mathematics. We get used to it. That's what you're doing when you learn mathematics. You get those two numbers, okay, the partial derivatives that together, if we're doing just two independent variables, we just have two, we have one airport, an x coordinate and a y coordinate. Those are our independent variables that we need to use, or that feed into our gradient. I'm kind of sleep deprived. What was I talking about? So you pick, geez. I'm really sleep deprived. I'm always going to be sleep deprived on Saturdays. That's just a warning. It's just the way that life is working out. What the hell was I talking about? Now that I'm thinking about what I was talking about, I can't remember what I was talking about. Okay, I was talking about the line. I picked the only line, and this is your brain on sleep deprivation. Okay, so the 6. Okay, so your two independent variables are, if you find the partial derivatives, you're going to, the two partial derivatives that compose the gradient function, those are going to be two numbers. It's going to be two scalars, okay? It's going to end up being, you can call it a rate, but it doesn't have to be like 6 over 1. You don't have to write the over 1. It's just, 6 is a rate. 6 over 1 might be 1 over 2, depending on your situation. Depending on where I place that first airport, that is what determines. So, but they're both, so one is a rate with respect to the, and it's like, you're on an objective function. You're not on a straight line, but your movements will be on a straight line. in certain circumstances, in my circumstance. Anyway, I know this is kind of hard to follow, but those rates, you have to use them both to figure out which direction is gradient descent, how to go downhill. Okay, so if we did our first score here, we placed an airport, we did an objective function, we got 46. We want to minimize. Okay, we're doing gradient descent. We want our score to be as low as possible because this represents how. The lower this is, the happier our cities are. And we can tell, like, we didn't put this city smack dab in the middle between these two cities, or this airport between these two cities. So we know that people aren't happy. We need them to be happier. Let's move the airport in, okay? How do you know which direction to go? I mean, you can see here that I moved down 1 and over 1. So I went down, my rate is -1. Why? Why is it -1? Because my gradient was +1, and 6 over 6. It was my gradient for y, my partial derivative for y over my partial derivative for x was 6 over 6. So if I want to increase, if I want to go uphill, if I want a higher score, I need to go 6 over 6 this way, which is 1 over 1, which is on a. I mean, you're looking at the mirror. Okay, this way on a Cartesian graph. If I want my score to go down, I go the opposite way, 1 over 1. That's why it was so spooky. Like 6 over 6, are you kidding me? Like these cities are not, they're not in a square. It's not like they're exactly, it was just spooky. It was just spooky, and rightly so. I mean, this doesn't intersect here. This doesn't intersect here. It was just spooky that I placed an airport there, and it just so happened that I landed right on the line, but it's my own fault for wanting round numbers. So the gradient told me to move 1 over 1 to increase my score, which would be this way, and -1 over 1 to decrease my score, which is what I want to do. So I moved over 1, so x -1, and y -1, okay? -1 over 1. And I just tried it, and I just, so I said, all right, I'm just going to do it again. I did the math again, and I'll show you where that math is. That starts, I mean, you can see where I started to get freaked out. Like, well, first of all, I identified a nice little spooky, suspicious coincidence there, but I knew that could be good. That 46 was my score. My first score, this 46, and then I'm going to be subtracting in the next. Okay, so you're seeing coincidence. This is a very, very, I should say, like, this is a toy problem. I'm doing gradient descent. I'm not using any software because I don't have to, because I deliberately set myself a very easy test problem. And that's what you should do, okay? And that's the right thing to do, but I'm not trying to represent this as being any hard. I know it's all chicken scratch and it looks like, all this math. It's not hard math. It's just like if you had to write down every single one of your thoughts when you were trying to figure out a problem. That's why this looks like a lot of stuff, but it's not a lot of stuff. All right. So then I just tried a state 2, and I said, I followed the rules. I followed gradient descent. I did exactly. Now this is called a step size. And deciding your step size. Okay. So I say in the title of these videos, it's like pages 19 to 122. We're not going to, we haven't dealt with 121, where they talk all about the real rubber meeting the road for gradient descent is choosing step size, and how do you not take forever, and how do you not overshoot your target and all this stuff. There's a whole different, but none of that is like we need to comprehend difficult mathematics. It's just like, okay, let's just get really good at this particular algorithm, which we don't want to we don't want to over optimize ourselves. Okay, so we're not talking about that, but that's what you're looking at here. This difference here, this movement of the airport from here, that's a step size. I could have moved it halfway, and I'd still be on my gradient descent line, which is, -1/2, or, back 1/2 and down 1/2 is the same as back 1 and down 1 in terms of rate. Okay, so my gradient, my two partial derivatives are telling me to head this way. And then I just did the math for this. So I got a new input a new argument to my objective function, 1710 instead of 1811. And so I started doing, I did so there's the end of 1811. So now I've got state 2. This is my second vector. It's just, the coordinates of the new airport. 1710, did the math on that. Okay, got a better score, 38, good. All right, let's just write up the partial derivatives again, just so we remember what we're dealing with. 17 plus h here, 10 plus h here. Subtract the score when h is 0, and then divide it. This is calculus. If you don't understand calculus, I can't teach it to you, but this is it. It's not as hard as it seems, and you should go learn it. And here, the hard part to calculate is the function of objective function of 17 plus h. and so holding y still here and then holding x still here, that's where the legwork comes in. But you can't calculate anything except reducing it to h. You can plug in your values and your only unknown is h, and you get this polynomial. And now I got another one. I got another polynomial. I was ready for it this time. The highest degree term was the same, it was 2, but this first degree term here was 2h instead of 6h. And then I was expecting this to be the same. I said, damn, okay, we can deal with this. This might turn out to be okay. It's starting to make sense. And I had looked at the map and started to convince myself this could really be the right answer. I really might not have made a mistake here. Then I plugged in a third airport. Okay, here's your third airport. 16.5, 9.5. I couldn't keep going a full step. I would have overshot the valley of my gradient here, the valley of my descent. I would have overshot it. And I knew that just because I have a simple map and I've got a little line between these two guys, and we're just dealing with two cities, so it's easy to understand. Easy enough. I know if you're not following it, it never seems easy, but trust me, if you look at these notes for half an hour, it's gonna make a lot more sense. Did the math on this one, calculate the objective function. Okay, what's our score? 37. I think at this point I started to know that 37 was the sweet spot, but I still didn't trust it. What did I say? And it's half the sum of the square of the distance between the cities. That means that this is starting to look like I did this correctly. Didn't need to write this stuff up again, blah, blah, blah. But I did realize here that the real test of whether I'd done it correctly is that the slopes, both of the partial derivatives should be 0. If I'm really at the perfect valley, if I'm at the perfect spot for this gradient descent, both of my slopes should be 0. My partial derivative, or my gradient, should not be telling me to go any direction unless I overshoot or I'm not there yet. So I did the math, and then I did this polynomial. I got this polynomial, and then jump over to the spreadsheet. This was the awesome moment. I only had to calculate 2 of these because I knew what was going on once I calculated one and saw it had the same similar inputs. And then I calculated the last one, and I got, sure enough, it converges on 0. Okay, so the partial derivative of f with respect to x sub a and y sub a both converge on 0 because they both have exactly the same polynomial and score term and same h trending towards 0. So that's how the math went. So that's when I knew, I confirmed, and and it was perfect. It worked out. I did this correctly. I wouldn't fly a plane written with this software that this chicken scratch. I wouldn't ride in a plane programmed by me on the basis of any of this. Not that plane flight has anything to do with gradient descent, but I wouldn't bet my life on it. But I'd bet. I'd bet my dog's life. I don't have a dog, but if I had a dog, I'd bet my dog's life on it. All right. So yeah, that's it. You can, this might look kind of scary, but all we're doing here in the Excel math, I don't know why I said Excel like that, in the spreadsheet math, is iterating on H. This is what makes this worth doing in a spreadsheet. You don't want to do this by hand. Look at this. I mean, this is ridiculous. This is what machines are for. Although I'm going to show you something in a second that's going to blow your mind. Okay, so we want to start with H as 1, and then, okay, cut it in half again. Just keep going towards 0 until we see, the shape of these things is, behaving as expected. And what's happening when we do the final calculation of the derivative? Is it trending toward a number that seems reasonable? Yes, it's not just reasonable, it's perfect. Do it again when you think you've made it home, you think you've placed your airport correctly. You should have no slope. That's what you get. 0 over 0 is actually undefined, but we don't have to use that ratio or that fraction. Okay, that's it. That's the math. Now, I've gone through the rest of AIMA4e, and there's nothing that's going to be more conceptually challenging than that. I don't think. I mean, if you can follow that, and I don't just mean follow it while I'm, machine gunning on a podcast, but look at the notes and see if you can follow the steps with the notes in hand. If you can do that, you'll be fine. It's not that the book is a breeze. It's just that there's no conceptual mathematics in it that's any more difficult than that. There are all kinds of crazy things in mathematics that are hard, and calculus is one of them. And gradient descent on the basis of calculus is it takes some. Yeah, I mean, but that's it. You've seen the hardest math that's in AIMA4e, in my humble opinion. Now, where are we at? So ECMP, English, code, math, progress. We move the math around because they don't code any of this stuff in 119 to 122, and I don't blame them. I mean, for two reasons. One, if I were to code the mechanics of what I did here, it would just be to prove that I can do it. It's stupid. It's not hard. There's nothing. I mean, coding the algebra, I don't even know. But I know that can be done. But that's not what you really want to do. The machine doesn't care. You have to give the machine you have to use numerical methods. You have to tell the machine. I don't know. Maybe I should be coding the algebra, but I'm not right now. But coding, having the code available, or knowing how to use the code that's already made for doing gradient descent. As much work as it was for me to do this toy problem, 2 cities, 1 airport, off center, and you kind of have some intuition to keep checking yourself to make sure you're not going crazy. That's a lot harder when you've got all the cities in Romania and you got 3 airports. You're not doing that you're not doing that in half a day like I did. It wasn't even half a day. Well, depending on how you count the hours. So we need, okay, so what are we gonna, well, if we're going to go to the code phase, look at this. They've got a 6-line function, including its declaration, a 6-line function that's a basic implementation of gradient descent. Now, I haven't read through this real Python article, but it just gets me excited. Like, man, I could rattle this off pretty quickly, but get this under my fingers in a reasonable amount of time. I haven't decided whether I'm going to do this, because the other thing is it's December 10th. There are other things that are worth doing in the book. There's other math worth doing in the book, even though it's not conceptually difficult. It would be good to just get it under our fingers. And there's other code, and really, there's the code that I think that we're not going to struggle with that code. To do that again, it would be just sort of like just to prove that we can do it. I don't want to get in that mode. All right, it's a waste of time. But the implementation of the pseudocode. They're doing things like they take the thing that is still sort of bothering me is that I can't really say that I've got a grasp of how they take a problem as an argument, and if they're doing it consistently throughout the book. If you look at the pseudocode, all of their functions after page 120 take as an argument a problem, just an object as a problem. Now, I have ideas about how they're doing that, how they're implementing that in Python, but they're just ideas. Just like with the gradient descent, like I understand it. I can explain it in English, but I've never done it before. Now I've done it before, so I'm thinking about doing that. I haven't decided yet. So that's it. Okay, enough. We've done the gradients and partial derivatives in the context of gradient descent. I'll make decisions. I don't know. I'm tired. I'll make decisions about tomorrow later. All the references will be in the PDF notes, retraice.com, retrace.com. This has been segment number 76. Signing off.